Hello everyone, welcome to my channel. In today's video, I'll talk about two special type of matrices. Number one, symmetric matrix, and number two, skew-symmetric matrix. So let's begin with the topic. Here is the definition. A square matrix A is said to be symmetric if A transpose equals to A. So here you are going to concentrate on two things. Number one, a matrix which we are talking about is a square matrix. We are talking about a special type of a square matrix for which this condition hold. This condition we can call it as condition of symmetry. Okay, and what is this condition of symmetry is if we take transpose of the matrix and that equals to itself, so that is nothing but condition of symmetry. Any square matrix in which if we take transpose and it remains same, so that will be called as symmetric matrix. Let's see example. So here is one example. What I suggest, you all can pause the video and take the transpose of this matrix. Are you getting transpose of the matrix as this? And now if we compare this A transpose with the A, both are one and the same. Okay. So here we get A transpose is equals to A. So this matrix A is nothing but symmetric matrix. Okay. So nothing but if you have to check a matrix is symmetric, what you need to do, you have to take its transpose, and if it transpose is equals to itself, so the matrix is symmetric. I have explained the same thing in the next slide with the help of a GIF image. Let's see that. So what I'm doing over here, I'm picking up rows and I'm putting into columns of its transpose. And now if you compare these two matrices, both are one and the same. So the given matrix A is a symmetric matrix. Now let's talk about how to construct an example of a symmetric matrix. For that, you are going to recall these 2 points. Number one, in a square matrix A is equals to Aij, diagonal elements are of the form Aii. Nothing but row index and column index is same for a diagonal matrix. And non-diagonal elements are of the form Aij, where I is not equals to j. So here is your 3 by 3 general matrix, and I am going to highlight diagonal elements first. These are nothing but your diagonal elements, and you can see for this diagonal elements, row index is same as column index. So we can say diagonal elements are of the form AII. And if we pick any one element from the remaining, that is nothing but a non-diagonal entry. Suppose I pick this A13. So A13, you can see row index is not same as column index. So I can say what? For non-diagonal entry, element is of the form Aij, where I is not equals to j. You can pick any element, any non-diagonal element. Suppose I pick A31, you can see I is not equals to j. You can pick A32, you can see I is not equals to j. So nothing but I'm trying to tell you a diagonal element is of the form AII, Nothing but row index is same as column index. And a non-diagonal element is of the form aij, where I is not equals to j. And the second point which you should recall, if A is equals to aij, then transpose of A is equals to aji. Nothing but row index and column index interchange. Okay. Let's begin with the main point for a symmetric matrix. For a symmetric matrix, we have A is equals to A transpose. Nothing but this is condition of symmetry. And if we have this, we can say Aij is equals to Aji. The thing which you see here in line number 2 is nothing but we are talking about equality of two matrices. And if we are talking about equality of two matrices, there are two conditions to hold. Number one, order has to be same. If we talk about order here, A and A transpose will have same order because A is a square matrix. Okay. So if A is matrix of order n by n, transpose of A will also have order n by n. Okay. So order we need not worry about. And second point of equality is each corresponding element should match. So nothing but by using that we can say Aij is equals to Aji for all Ij. For each Ij value, Aij will equals to Aji. What I am going to do with this condition? I am going to take this condition with two types of elements which we have in square matrix, diagonal element and non-diagonal element. If I apply this condition on diagonal element, you all know diagonal elements are of the form aii, row index equals to column index. So this j is becoming I over here, you can see. So this j which is on the right side will also become I. So nothing but we get on diagonal aii equals to aii. So on diagonal we get this aii equals to aii means there is nothing special about it. So what I'll say, you can have anything on the diagonal. You can have positive number, you can have negative number, you can have zero, doesn't matter. So there is nothing special about diagonal entries of a symmetric matrix. You can have anything on the diagonal of a symmetric matrix. So on diagonal we get aii equals to aii, and it means there is nothing special about diagonal entries. And what about non-diagonal entries? So for non-diagonal entries are of the form aij, where I is not equals to j. So for aij, we are getting a condition that aij will match with aji. Nothing we, nothing but if I pick one particular element, suppose I pick a13, a13 is a non-diagonal entry. So this a13 will match with a31. Nothing but while constructing an example, an element which is present in first row third column that will match with an element which is present in third row first column. So these two elements will be same. So let me pick another one. Suppose I pick a non-diagonal entry A23. So the element which is present in second row third column, that will be same as the element present in third row second column. Okay. So there is something special about non-diagonal entries. I usually say cross diagonal entries should match. I call this type of thing as cross diagonal entries. Let us see how to construct that example. So for the construction, we got 2 points. Number one, there is nothing special about diagonal entry. We can have anything on the diagonal. So suppose I take a positive number, a negative number, and a neutral number, nothing but 0 on the diagonal. I can have anything on the diagonal, so I have taken all three types of numbers on the diagonal. And after that, what I have to do? I have to put cross diagonal entries same. So suppose I put here 7. So cross diagonal entry of this 7 is this element. So I'm going to put 7 over here. How I am getting this? This element is nothing but A12. So that will equals to A21, and this is nothing but A21. Suppose I put any number here 8. So I have to put cross diagonal same. So cross diagonal entry of this 8 is here. So I have to put 8 over here. This is what your A13, and according to the condition that will equals to A31, and this is nothing but your A31. Suppose I put here -2. So cross diagonal entry of this -2 is here. So I should put -2 over here. This is your A23, and according to the condition A23 will equals to A32. So I should put A32 same, and this is nothing but your A32. And this is how you construct example of a symmetric matrix. So here I have used different color combination to explain the same thing. I have used first of all a black color to denote a diagonal entries, because there is nothing special about this. So that's why I have used a black color. We can have anything on the diagonal. And after that, these two elements are of the same color because they will match. Okay. And these elements are of same color because they should match. And these two elements I'm denoting by same color because they will match for the construction of symmetric matrix. And you all can see this matrix, this element is actually A21, but I'm not writing A21 because A21 will equals to A12. So instead of writing A21, I'm writing A12. Okay. And similarly for the other. And here is another example. You can have anything on the diagonal. So I have taken this elements on the diagonal. I have taken one positive number. I have taken one 0, which is neutral element. I have taken one negative number. And after that, these two elements are same. These two elements are same. And these two elements are same. So this is how you construct example of a symmetric matrix. I hope the idea to construct example of a symmetric matrix is clear to you. So you all can try an example of order 3 by 3, an example of order 4 by 4 on your own. And if you come across any issue while constructing example, let me know in the comment section. I'll try to explain in a different way in another video. So now let's talk about second special type of matrix, skew-symmetric matrix. Here is the definition. A square matrix A is said to be skew-symmetric if A transpose is equals to minus of A. Again, you are going to concentrate on two things. We are talking about special type of square matrix for which transpose equals to its negative. I can multiply this condition. I can multiply on both the sides by -1. So if I multiply both the sides by -1, this LHS will become minus of A transpose, and this RHS will become minus of minus A. And minus of minus A is nothing but A. So nothing but the same condition can also be written like this. A is equals to minus of A transpose, and I use this second condition more preferably. Okay, so I'm going to use everywhere this second condition instead of using the first one. What I'm telling you in the first condition, I'm telling you transpose of the matrix will equals to its negative, and in the second one I'm telling you a matrix will equals to its negative transpose. So nothing but a square matrix A is said to be skew symmetric if that matrix A will equals to its negative transpose. Now let's see one example. So here is one example I have taken. What I suggest, you all can pause the video and compute its negative transpose. First you compute its transpose and after that you compute its negative. Nothing but you have to change the sign of each element of A transpose. Now you can pause the video and do it. I hope you all must have got this. And after that, you're going to compare this minus of A transpose with this A. So if we compare, you can see all elements are same. All elements are matching. So nothing but we have A is equals to minus of A transpose. Nothing but the given matrix A is skew symmetric. I have explained the same thing by using again a GIF image. You all can see that in the next slide. Here it is. So I am picking up rows and putting into columns of A transpose to get its transpose. So there is one correction over here. This minus 206 minus 20 minus 6 I'll put into second column. So here I missed that minus sign. So there will be a minus sign over here. So this is about A transpose. What I'm supposed to do next, I have to compute its negative. So for computing minus of A transpose, what I'm supposed to do, I should change the sign of each element. Positives will become negative and negatives will become positive, like this. And sign of this will also change. So here you'll get plus 6, not minus 6. Now if you compare these two matrices A and A transpose, you can see this first row is matching with the first row, the second row is matching with the second row, this third row is matching with the third row. Nothing but the two matrices are one and the same. So A is equals to minus of A transpose. So this given matrix A is skew symmetric matrix. Now let's talk about how to construct example of a skew symmetric matrix. For that, again, those two recall points. Number one, diagonal entries are of the form AII, nothing but row index is equals to column index. And for non-diagonal elements, the non-diagonal elements are of the form Aij, where I is not equals to j. And the second point, if A is equals to Aij, then A transpose equals to Aji. Nothing but row index interchange with the column index. And let's come to the main point. For a skew-symmetric matrix, the condition is A is equals to minus of A transpose, and that will give you Aij is equals to minus of Aji. And again we are talking about here equality of two matrices, and since both are square matrices, A is square matrix, A transpose will also be a square matrix of same order. So we need not worry about whether orders are same or not. And the second point of equality of matrix will give you Aij is equals to minus of Aji for all Inj. For each Inj, this condition will hold. And if it is holding for each, we are going to do this, we are going to apply this on two types of element, diagonal and non-diagonal elements. Let's talk about diagonal element first. We all know diagonal elements are of the form aii. So this j which is on the left side will become I. So the j which is present on the right side will also become I. So we get aii equals to minus of aii. So what is the meaning of this? The meaning is the element is equals to its negative. Can you imagine an element equals to its negative? There is only one such element, nothing but 0. 0 equals to its negative. 0 equals to minus 0. Okay. So this this gives you aii equals to 0. Now this is one way of thinking. The other way is you can add aii on both the sides. So if I add aii on both sides, on the left side I'll get aii plus aii is equals to, on the right side I'll get aii minus aii, and this right side will result into 0 and this left side will result into 2 times aii, and this will give me aii equals to 0. And what do you understand by this? Nothing but diagonal entries are 0. We have to pick, we have to put diagonal entry as 0. We can't have non-zero entry on diagonal for the construction of example of a skew-symmetric matrix. So for a skew-symmetric matrix, diagonal entry is always 0. Okay, here it is. Let's talk about non-diagonal entry. So for non-diagonal entry, aij equals to minus of aji. Let's talk about one such entry. Suppose I talk about A13. So A13 will equals to minus of A31. Nothing but an element which is present in first row third column will equals to negative of element which is present in third row first column. So suppose I have A13 as let's say minus 2. So A31 will equals to minus of A13, which will equals to 2. You have to put cross diagonal entry as a negative of each other. Okay, I call it as cross diagonal entry to that, and this time you are going to put a negative of each other. If I have a plus 2, so I have to put cross diagonal entry minus 2. If I have minus 3, I have to put cross diagonal entry as 3. Okay, so let's construct one example over here of a skew symmetric matrix. For the construction, we note 2 points. Number one, diagonal entries has to be 0. So first of all, you are going to put 0 on the diagonal, and after that, cross diagonal entries has to be negative of each other. So suppose I put minus 2 over here, negative of minus 2 is 2, so you have to put cross diagonal as 2. Suppose I have 7 over here, so I have to put cross diagonal, it's negative, minus 7. Suppose I have 6 over here, so I have to put negative of this, which is minus 6 over here. So this is how we construct example of a skew-symmetric matrix. To explain the same, I have used this color combination again over here. First of all, diagonal 0. All diagonal entries has to be 0. then this cross diagonal entry will equals to the negative of each other. A13 is equals to minus of A31. A23 will equals to minus of A23. Okay. So you all can see this element is actually A21, but I am not writing A21, I am writing minus of A12. That is happening because of the condition. Condition is A12 is equals to minus of A21. And if it is minus of A21, what I can have? I can even say this as A21 is equals to minus of A12. I am multiplying both the sides by minus 1. So instead of writing this A21, I am writing minus of A12 over here. And similarly for the others. Let's say example. So here it is. Here is your an example of a skew-symmetric matrix. Zeros on the diagonals and cross diagonal negative of each other. Minus 2, negative of minus 2 is 2. 6, negative of 6 is minus 6. Minus 5, negative of minus 5 is 5. So I hope idea of construction is clear to everyone. How to construct example of symmetric matrix and skew symmetric matrix is clear to you. So here is your exercise. You are going to give example of symmetric and skew symmetric matrix of order 3 by 3 and 4 by 4. And obviously you have to construct your own example. You are not going to give example which is already there in the video. You have to produce your own example. And if you have any queries, let me know in the comment section. I think this much is enough for the session. Thanks to all my viewers. Thanks for watching.